Tonight, we're going to explore a star so large that if it took the place of our Sun, you would no longer have a solar system. You would have a single, glowing thing, and the planets would simply be somewhere inside it. Mercury, gone. Venus, gone. Earth, the ground beneath you, the air you are breathing right now, all of it folded somewhere deep within the star's outer layers. Mars, the asteroid belt, the great striped giant Jupiter, all swallowed. And the edge of this star, the faint outermost reach of it, would stretch onward through the dark until it came to rest almost exactly at the orbit of Saturn. That is not a thought experiment. There is a real star, catalogued and studied, that is genuinely this size. Astronomers call it Stephenson 2 to the 18. It is a red supergiant, an aging star near the end of its life, and it sits roughly 19,000 light-years away from us, toward a quiet, dust-veiled patch of sky in the constellation Scutum, the Shield. Its radius is often given as around 2,150 times the radius of the Sun. And if you take that number and ask how many suns you could pour inside a sphere that wide, the answer comes to something close to 10 billion. 10 billion suns held inside the volume of one star. It is the kind of number that does not really fit in the mind, and that is all right. You are not meant to grasp it all at once tonight. We are going to take it slowly, the way you might unfold a very large map one corner at a time, until the whole thing is spread out in front of you, and somehow feels gentle instead of overwhelming. So let me say first what this is not. This is not a story about danger. Stephenson 2 till 18 is 19,000 light-years away, which is so far that the light reaching your eyes from it tonight, if you could see it at all, left the star around the time the last ice age was loosening its grip on the Earth. Whatever this star does, it cannot reach us. It poses no threat to anything you love. There is nothing here to be afraid of. There is only something very large and very strange, sitting far out in the dark, waiting to be understood a little better. And it is the strangeness, not the size, that we are really here for. Because here is the thing that the size alone never tells you. That headline number, 2,150 times the Sun, is not a settled, carved-in-stone fact. It is the high end of a contested range. The star is buried behind so much interstellar dust and sits at a distance so genuinely difficult to measure that careful astronomers will tell you its true size could be meaningfully smaller or could be larger, and that the honest answer carries an uncertainty most people never hear about. The number is real. The doubt around it is equally real. And the doubt, it turns out, points to something more interesting than the number ever could on its own. There is more underneath the size too. This star is so enormous and yet holds so little material for its volume that it is, on average, 100 million times thinner than our own Sun. Thinner, in fact, than the best vacuum we can create in a laboratory here on Earth, which raises a quiet and surprisingly deep question, one we will sit with later tonight. If a star is that diffuse at its edges, where does the star actually end? What does it even mean to draw a line and say, here is the surface. Beyond this point, it is no longer the star. And there is one more thread, the oldest and most human one. Stephenson 2 till 18 is only the latest in a long line of stars that have each, in their turn, been called the largest ever found. Betelgeuse held a version of that title. So did a star called VY Canis Majoris. So did one called UY Scuti. And every single one of them, when astronomers looked again with better instruments and more careful methods, turned out to be somewhat smaller than first believed. Each crown came off quietly. Each record came with an asterisk that only became visible later. The real story of the largest star is not really about any one star at all. It is about how patient, careful measurement keeps gently humbling us again and again across the decades. So that is where we are going tonight. We will start close to home with what a star actually is and why it has a size at all, which is a less obvious question than it sounds. We will walk the long, humbling history of the largest known star, meeting each former record holder in turn, and watching how each one taught us something new about how hard this kind of measurement really is. We will talk about why distance, of all things, is the single hardest honest problem in astronomy, and why a small error in distance becomes an enormous error in size. Then we will arrive at Stephenson 2-18 itself, the star that was very nearly overlooked, set aside in a catalogue for years because it seemed too bright to make sense. We will let its scale unfold slowly, planet by planet, out toward Saturn. We will explore that strange, fog-soft boundary where the star fades into space without ever quite ending. We will look at the physics it seems to strain, the limit it appears to sit just past, and what that really tells us, which is gentler and more interesting than it first sounds. And finally, we will follow it forward in time, toward the brilliant end that waits for every star this large, and then come quietly back home, to your room, to your breath, to the small and steady ground beneath you. There is no rush in any of this. Nothing tonight needs your effort. If you drift off somewhere in the middle, you will have lost nothing, because the wonder of it does not depend on you holding every number in your head. It only asks that you let the scale wash over you a little, the way you might lie back in the grass on a clear summer night, and feel, just for a moment, how much larger the universe is than the day you spent inside it. So settle in. Let your shoulders come down from wherever they have been holding all day. Find the position that feels easiest, and let your breathing slow to whatever pace it wants to find on its own. We are going out past the planets tonight, past the edge of everything familiar, to a single enormous star sitting quietly in the dust of the inner galaxy. And as we go, we are going to discover that its size, as staggering as it is, may be the least surprising thing about it. Let's begin. Before we can understand a star that is too large, it helps to sit for a moment with a simpler question, one that sounds almost childlike until you really look at it. Why does a star have a size at all? Why is the sun the width that it is, and not twice as wide, or half? A cloud of gas in space has no obvious reason to settle on any particular shape. And yet every star you have ever seen has found a size and mostly held it, steady, for a very long time. The answer to why is the quiet engine underneath everything we are going to talk about tonight. So let's take it slowly. A star is at heart a balance between two enormous forces that are always pushing against each other. The first is gravity. A star contains a tremendous amount of material, and all of that material is pulling inward, toward the center, trying to collapse the whole thing down into the smallest space it can. If gravity were the only force at work, a star would simply crush itself into a point. Nothing that large could hold its shape against its own weight. But there is a second force pushing the other way, outward, and it comes from the heart of the star. Deep in the core, the pressure and temperature are so extreme that hydrogen, the lightest and most common element in the universe, is squeezed and heated until its atomic nuclei fuse together to form helium. In the Sun, the core reaches around 15 million degrees, and at that temperature, this fusion runs steadily, releasing energy as light and heat. That energy flows outward through the star, and as it goes, it pushes. The outward flow of all those photons, all that radiation streaming up from the core, presses against the inward pull of gravity. When these two forces come into balance, the star stops collapsing and stops expanding. It simply holds. Astronomers call this hydrostatic equilibrium, which is a formal way of saying that at every layer inside the star, the weight pressing down from above is matched, almost exactly, by the pressure pushing up from below. That balance is what gives a star its size. The sun is the width it is, because that is where the pushing out and the pulling in happen to meet. And the place where they finally settle, the visible surface we see when we look at the sun, has a name worth knowing tonight. It is called the photosphere, from the Greek for light and sphere, the sphere of light. It is not a solid shell, nothing you could ever stand on. It is simply the layer where the gas finally becomes thin enough that light can escape and travel freely out into space. Below it, the star is opaque, the light trapped and bouncing for thousands of years before it works its way up. Above it, the gas thins into the star's faint outer atmosphere. The photosphere is the line we draw and call the edge. For the sun, that line is reasonably clear. For the star we are heading toward tonight, it is not clear at all. For most of a star's life, this balance is patient and quiet. The sun has been holding it for about 4.5 billion years and will hold it for billions more. As long as there is hydrogen in the core to fuse, the outward push stays strong, gravity stays answered, and the star stays steady. This long, stable stretch is called the main sequence, and it is where stars spend the vast majority of their lives, simply shining in balance, doing nothing dramatic at all. But hydrogen does not last forever, and what happens when it begins to run out is not a slow fade, but a result that seems at first deeply counterintuitive. When the core finally exhausts its hydrogen, the fusion in the very center slows and falters. The outward push weakens, and gravity, which has been waiting patiently this whole time, begins to win. The core starts to contract, squeezing down on itself, and as it contracts, it heats up further. That extra heat does something almost paradoxical. It reaches the layer of hydrogen still surrounding the spent core, a shell of fresh fuel that had never been hot enough to fuse before, and now, suddenly, it ignites. A shell of hydrogen fusion switches on around the shrinking core, and that shell burns fiercely. It pours out far more energy than the old core ever did, and that flood of new energy pushes outward on everything above it. The outer layers of the star, the vast envelope of gas surrounding the core, get driven outward and begin to swell. The star inflates. It grows and grows, expanding far beyond its old main sequence size, sometimes by factors of hundreds. The sun, in its time, will balloon outward until it reaches roughly to the orbit of the Earth. Here is the gentle, counterintuitive part. As the envelope expands, it also cools. The same amount of light is now spread across a far larger surface, so each patch of that surface glows less hotly, and cooler stars glow redder, in the same way the embers of a fire shift from white hot to a deep, dim red as they fade. A surface that once burned at 5,000 or 6,000 degrees drops toward 3,000. The star turns from white or yellow to a soft ember red. It has become a red giant. For a star like the sun, that is roughly where the swelling stops. But for stars that begin their lives much heavier than the sun, far more massive, with far more fuel and far stronger gravity to work against, the same process runs to a much greater extreme. These stars do not merely become red giants, they become red supergiants, and the scale is on another order entirely. The envelope spreads outward, not to the orbit of the Earth, but vastly beyond, hundreds of times wider than the Sun, sometimes more. The outer layers grow so thin, so distended, so far from the core that holds them, that the star stops resembling a solid ball of fire at all. It becomes something closer to an enormous, faintly glowing cloud, with a small, dense, furiously burning core buried somewhere deep at its center. That image is worth letting settle, because it is the key to the whole night. A red supergiant is more cloud than sphere. Its core is compact and intense, but its outer reaches are a thin, swollen haze, held so loosely that the very idea of a firm surface begins to lose its meaning. The photosphere, that tidy line we drew for the Sun, becomes harder and harder to locate, as the gas thins out so gradually that no single layer announces itself as the true edge. This is the family that Stephenson 2-18 belongs to. It is a red supergiant, an aging massive star that has long since left the steady balance of its youth, whose core has run through its easy fuel, and whose envelope has swollen outward into that vast, diffuse haze. It is the same process that will one day swell our own Sun, simply taken to an extreme so great that it almost stops feeling like the same kind of object at all. And so the question we started with, why a star has a size, turns out to have a quietly unsettling answer when you reach the supergiants. For the Sun, the size is clear, set by a balance we can point to, and a surface we can measure. For a star like Stephenson 2-18, the balance still holds, in its own loose and extended way, but the surface has gone soft. The edge has become a gradient, and that means before we can ask how large this star is, we have to ask how large the rules of physics will even allow a star to become, and what happens when one appears to ignore them. That ceiling, the one astronomers spent decades believing a star could not cross, is where we go next. For a long time, astronomers carried a quiet expectation about how large a star could grow. Not a hope, not a guess, but something that fell out of the equations when you sat down and worked through the physics of these swollen, aging giants. Push a star past a certain size, the model said, and it should no longer be able to hold itself together. There seemed to be a ceiling, somewhere in the neighborhood of 1,500 times the radius of the Sun, beyond which a star simply should not be able to remain a star for very long. To feel why, it helps to return to the balance we talked about, gravity pulling in and radiation pushing out, and then to follow what happens to that balance as a star swells into a supergiant. Gravity has a particular and important habit. It weakens with distance, and it weakens quickly. The pull you feel from any object falls off as the square of how far away you are. Move twice as far from the center of a mass, and its grip on you drops not to half, but to a quarter. Move 10 times as far, and it drops to 100th. This is one of the oldest and most reliable rules in physics, and it has a gentle consequence for a star that is busy inflating itself to enormous size. As a supergiant's envelope balloons outward, the outermost layers of gas end up sitting an immense distance from the dense core that holds them. And because gravity falls off so steeply with distance, the hold that the core has on those distant outer layers becomes astonishingly weak. The gas at the visible surface of a red supergiant is bound to the star by a gravity far fainter than the gravity you feel standing on the Earth. It is barely tethered at all. It is more like mist clinging to the top of a mountain than like a rock sitting firmly on the ground. Now bring back the other force. Radiation, the river of light streaming outward from the core, is still pushing on all of that gas. Light carries momentum. We rarely notice this in daily life, because the push of ordinary light is so tiny, but inside and around a star, where the light is overwhelmingly intense, that outward pressure is a genuine and powerful force. It presses on every layer of gas it passes through, nudging it outward, away from the center. So picture the situation at the surface of a very large supergiant. The outward push of radiation stays strong, because the star is luminous and the light is fierce. But the inward grip of gravity has grown weak, faint, because the gas is so far from the core. And there comes a point, as the star grows larger and larger, where these two are no longer in comfortable balance. The outward push begins to rival the inward hold. When that happens, the star can no longer keep its outermost layers. The radiation drives them off into space faster than gravity can pull them back. The envelope begins to disperse. That tipping point is what set the ceiling. Run the calculations through the standard models of how supergiants are built, the ones astronomers refined across the 20th century, and you find that somewhere around 1500 solar radii, the loosely bound outer envelope should start losing its battle against the star's own light. Past that size, the star should shed its outer layers faster than it can hold onto them. It should not be able to sit calmly at a radius much larger than that. The ceiling was not a wall someone built. It was simply where the numbers said the balance gives way. And here is the part worth holding gently, because it matters for everything that follows tonight. That ceiling was never a law of nature in the way that, say, the speed of light is a law. It was an expectation drawn from models, and models are simplifications. To make the mathematics workable, those calculations assume certain tidy things about a supergiant, that it was smooth, a uniform sphere, the same in every direction, that its gas absorbed and blocked light in a simple, even way, that it behaved more or less like a clean and well-mannered ball of glowing gas. Real stars are rarely so well-mannered, and so the 1500 solar radii ceiling was always best understood as a soft guideline rather than a hard barrier. It described where a simple, idealized star should run into trouble. It was honest about the average case, the expected case, the case that fit neatly into the equations. What it could not promise was that no real star, with all its messiness and irregularity, would ever be found sitting on the far side of the line. For a good while, though, the guideline held up. The larger stars astronomers found tended to fall at or below that ceiling, more or less where the model said they should. The expectation looked sound. A supergiant might reach 1,000 solar radii, or 1,200, or push toward 1,500. But beyond that, the sky seemed to stay quiet. The boundary that physics had sketched appeared to be respected by the universe. And then a star turned up well past it, not a little past it, not nudging the edge of the uncertainty. If its often quoted size is anywhere near right, Stephenson 218 sits at something like 2,100 solar radii, which is not just over the ceiling but far above it, well beyond the point where the simple models say a star should be able to keep its outer envelope at all. By the tidy version of the rules, the version drawn for clean, uniform, well-behaved spheres of gas, a star this large should be quietly dispersing itself into space, rather than sitting there as a coherent object. That is the heart of the phrase in tonight's title, the idea that this is a star that, in some sense, should not exist. It is not that physics has broken. It is that this star sits on the wrong side of a line our simplest equations drew, and in doing so, it is quietly telling us that those equations were written for neater stars than this one. The ceiling did not fall because the universe broke a rule. It softened because we discovered the rule had been describing an idealized star all along, and the real ones are stranger and more porous and more forgiving than the clean version allowed. How a star manages to exist above that ceiling at all is a question the physics answers in a way that is quieter and more interesting than the ceiling itself suggested. For now, it is enough to hold the shape of the puzzle. There was a ceiling. It was reasonable, and it was respected, until it wasn't. And the story of how we came to find the star that broke it is, before anything else, a story about how astronomers spent a century slowly, carefully, learning to measure the largest stars at all, and being humbled every time they thought they had it right. That long and patient humbling is where we turn next. Step outside on a clear winter evening, look toward the south, and find the constellation Orion, the hunter, with his 3-starred belt hanging at a tidy slant across the middle of him. Now look up and to the left of that belt, to the hunter's shoulder, and find the star burning there with a color the others around it do not share. While most stars glitter white or blue-white, this one glows with a warm, unmistakable orange-red, like a coal that has been breathed on. That star is Betelgeuse, and it is the gentlest place to begin our long lineage of giants. Because of all the enormous stars we will meet tonight, it is the one we can actually see. Betelgeuse sits roughly 700 light-years away. By the standards of tonight, that is practically next door. It is close enough and large enough that astronomers have managed something extraordinary with it, something they can do for almost no other star in the sky. They have resolved its disk. They have taken images in which Betelgeuse is not merely a point of light, the way every other star appears even through the finest telescope, but an actual circle, a face, a surface with features on it that can be studied and watched over time. That may sound like a small thing, but it is worth pausing on, because it is genuinely rare. The stars are so distant that nearly all of them, no matter how powerful the instrument, remain stubbornly point-like. They are simply too far away to show as anything more than a dot. Betelgeuse is one of the very few exceptions, one of a tiny handful of stars whose actual surface we have been able to picture. When the Hubble Space Telescope turned toward it in the 1990s, it captured an image showing the star as a glowing disk with a bright, mottled patch across it, a real photograph of the surface of another sun. Later instruments, using a technique called interferometry, that links several telescopes together to act as one enormous eye, sharpened the view further, revealing a surface that churns and changes, dappled with vast cells of rising and sinking gas, each one larger than the entire orbit of the Earth. So how large is Betelgeuse? The honest answer is that it depends on when you ask, and this is the first quiet lesson of the lineage. Betelgeuse is not a fixed, steady ball. It is a pulsating star, slowly swelling and shrinking and brightening and dimming over time, the way a chest rises and falls in slow breath. Depending on where it is in that rhythm, and depending on which method you trust, its radius is usually given somewhere in the range of 700 to perhaps 1,000 times the radius of the Sun. If it sat where our Sun sits, its glowing surface would reach out past the orbit of Mars, swallowing Mercury, Venus, the Earth, and the red planet beyond. Even at the low end of that range, Betelgeuse is a true supergiant, vast beyond easy imagining. And yet, set against the stars still to come tonight, it is almost modest. That is exactly why it belongs at the start. Betelgeuse is the clean case. It is the giant we can see clearly, measure directly, and study at our leisure, close enough that the usual fog of distance and dust barely troubles us. Everything past Betelgeuse gets harder. Every star further out in this lineage is more obscured, more uncertain, more a matter of inference than of sight. Betelgeuse is the last one we get to simply look at. And even here, even with the one supergiant we can see most clearly of all, the universe found a way to remind us how little we truly have pinned down. In late 2019, something happened to Betelgeuse that astronomers had not anticipated. The star began to dim, not by a little. Over the following months, it faded until it had lost something like 2/3 of its usual brightness, dropping so noticeably that even casual stargazers could tell that Orion's shoulder no longer burned the way it used to. The event came to be called the Great Dimming, and for a short while it set off a wave of quiet speculation. Betelgeuse is an old star near the end of its life, the kind of star that will one day end in a supernova. Was the dimming a sign that the end had begun? Were we watching the prelude to one of the most dramatic events the night sky can offer? It turned out to be something subtler and, in its own way, more interesting. As astronomers studied the dimming closely, using the very ability to resolve Betelgeuse's disk that makes it so special, they pieced together what had most likely happened. The star had belched out a great cloud of gas from its surface. An enormous bubble of material lifted off the star and flung outward. As that cloud drifted away and cooled, some of it condensed into dust, and that dust hung in front of part of the star like a passing veil, blocking and dimming the light reaching us. Combined with a cooler patch on the surface beneath it, the veil dimmed the star dramatically for a season. Then, over the course of the following year, the dust dispersed, the star recovered, and Betelgeuse returned to its familiar brightness, shining once again at the hunter's shoulder. It was not the beginning of the end. It was the star simply doing what these aging giants do, shedding pieces of itself in great irregular gusts. But the episode carried a lesson that runs straight through tonight's story. Here was the best-studied supergiant we have, the one star of its kind we can actually image, and even it managed to surprise us. Even Betelgeuse, watched for centuries, photographed as a disk, monitored night after night, still had something to show us that we had not predicted. If the star we can see most clearly can do that, it should make us gentle and humble about the stars we can barely see at all. And there is a deeper unease folded into Betelgeuse, the same one we will meet at every stop tonight. Even its size, that range of 700 to 1,000 solar radii, is not perfectly settled. It depends on the star's distance, which is itself not perfectly known, and on exactly which layer of that puffy, pulsating, ill-defined surface you choose to call the edge. For the clean case, the easy case, the one star we can resolve, the number still comes with a quiet asterisk attached. The measurement is good. It is simply not as certain as we might like, and it never quite is. That is the pattern that will follow us out into the dark tonight. Each giant we meet will be a little further away, a little more veiled, a little harder to pin down than the last. Each one's size will rest on a chain of careful inference, a distance estimated, a brightness measured, a temperature judged, a radius calculated from all of them together. And each link in that chain carries its own small uncertainty, which means that as we move outward, away from the stars we can see, and toward the stars we can only deduce, the numbers grow ever larger and ever softer at the same time. Betelgeuse, then, is our anchor, the shoulder of Orion, hanging there on a winter night, a real surface we can almost reach out and read. Hold that image as we go, because from here on, the seeing gets harder. The next stars in the lineage are buried deeper in their own ejected clouds and in the dust of the galaxy between us. and with them the questions begin in earnest. The first of them was a star so wrapped in the gas it had shed that astronomers could not even agree where the star ended and its own breath began. That star is where we go next. There is a star low in the southern winter sky, in the constellation Canis Major, the great dog that follows Orion across the heavens. You would not pick it out with your eye. It is far too distant and far too dimmed by the dust between us to be a casual sight. But it is one of the most remarkable objects in our galaxy, and for a long time it was thought to be the largest star known. Its name is VY Canis Majoris, and where Betelgeuse taught us about pulsation and surprise. This star teaches us something stranger and softer. It teaches us that sometimes you cannot tell where a star ends, because the star will not let you. VY Canis Majoris sits roughly 3,900 light-years away, more than 5 times farther than Betelgeuse. At that distance, we lose the ability to resolve its surface in any clean way. But distance is only part of the problem. The deeper difficulty is something the star made for itself. VY Canis Majoris is one of the most dramatic shedders of material in the known sky. Over the long, slow centuries of its old age, it has thrown off enormous quantities of its own gas and dust, expelling them in great irregular outbursts, and all of that ejected material now hangs around the star in a vast, glowing, lopsided cloud. Where most stars sit in relatively clear space, this one is wrapped in a nebula of its own breath, a sprawling, asymmetric cocoon of the stuff it used to be. And that creates a genuine and rather beautiful problem. When you look toward VY Canis Majoris, you are not looking at a clean ball of star against empty dark. You are looking at a bright core embedded in layers of gas it has cast off. Gas that glows and scatters light and blends seamlessly into the star itself. So where does the star end? Where is the line between the supergiant and the debris it has exhaled? The honest answer, for a long time, was that nobody could say with confidence. The boundary was not sharp. The star faded into its own surroundings by degrees, and depending on where you chose to draw the edge, you got very different answers for its size. In the mid-2000s, some estimates placed VY Canis Majoris at around 1,800 times the radius of the Sun. If that figure had held, it would have been the largest star in the known sky, by a considerable margin. It did not hold. As astronomers worked to disentangle the genuine photosphere from the surrounding shed material, the estimate came down. More careful later work, separating the star proper from the nebula wrapped around it, settled on something closer to 1,400 solar radii. Still immense. Still one of the largest stars we know, but meaningfully smaller than the early headline, and smaller for a telling reason. The star had not changed. Our ability to tell the star apart from its own cloud had improved. That is the lesson VY Canis Majoris leaves us. Its crown did not come off because it shrank. It came off because we learned to see it more clearly, to peel away the haze of its own making and find the real boundary underneath. The size fell, but what fell was never the star. It was the generosity of our earlier guess. Now travel a little way across the sky to the constellation Scutum, the same dust-shrouded shield where Stephenson 2-18 waits for us later tonight. There is a star there that carries perhaps the most dramatic cautionary tale in this whole lineage. A star whose size did not gently settle downward, but was, in a single stroke, very nearly cut in half. Its name is UY Scuti, and its story is really the story of how one measurement, the hardest measurement in all of astronomy, can hold up an entire reputation and then quietly pull it down. UY Scuti had a long and unremarkable life in the catalogues. It was first recorded by astronomers in Bonn, Germany, in 1860. Noted as a variable star whose brightness changed over time, and then set aside for the better part of a century and a half. One of countless entries, logged and shelved. Nothing in the record suggested it would one day hold the title of largest known star in the Milky Way. That changed in 2013. A team of astronomers working from the University of Granada in Spain studied UY Scuti carefully and worked out a distance to it, placing the star at something like 9,500 light-years away. And distance, in astronomy, is the master key. Once you believe you know how far away a star is, you can convert how bright it merely appears in your telescope into how bright it truly is, its real outpouring of light. And once you know a star's true brightness and its temperature, you can calculate its size, because a cooler star of a given brightness must be enormous to give off that much light from such a dim surface. Run UY Scuti's numbers through that chain using the 2013 distance, and you arrived at a radius of roughly 1,700 times the Sun. With that, UY Scuti was crowned. For years afterward, it was the star that topped the list, the reigning largest known star in the Milky Way. Then came Gaia. Gaia is a space telescope, launched by the European Space Agency, with one extraordinary specialty. It measures the positions of stars with a precision no instrument before it could approach, and from those precise positions it measures distances directly using the oldest and most trustworthy method we have, called parallax. The idea behind parallax is something you can feel right now. Hold a finger up at arm's length and look at it with one eye, then the other. Your finger appears to jump against the background. Nearer things shift more, farther things shift less. Gaia does the same thing with stars, watching how they appear to shift as the Earth carries it from one side of the Sun's orbit to the other, and from the size of that tiny shift, it reads off the distance. No assumptions about brightness, no chain of inference, just geometry, the cleanest measurement there is. In 2018, Gaia released a great catalogue of these measurements, and tucked within it was a new distance for UY Scuti. And it was not 9,500 light-years. It suggested the star was considerably closer, perhaps only around 5,000 light-years away, roughly half the distance the 2013 work had assumed. And distance, remember, is the master key. Halve the distance, and the star is far less bright than you thought, because it did not have to shine across nearly so much space to look the way it does. And a far less luminous star is a far smaller star. When the new distance was carried through the same calculation, UY Scuti's radius fell from 1,700 solar radii towards something closer to 750. In the space of a single data release, the largest star in the galaxy had been cut to less than half its former size. But, and this matters, the story does not end with a clean correction. Gaia is a marvel, but even Gaia struggles in this particular part of the sky. The constellation Scutum lies along the crowded, dusty plain of our galaxy, jammed with stars and choked with interstellar haze. And in regions like that, even Gaia's exquisite parallax measurements carry larger uncertainties than usual. The light is dimmed, the field is crowded, and the geometry gets harder to read cleanly. So the honest summary is not that UY Scuti was definitively shrunk. It is that UY Scuti's size fell into genuine dispute. One careful measurement said one thing. Another careful measurement said something very different, and the truth sits somewhere in a range we still cannot close tightly. The crown did not pass cleanly to a new holder. It simply became unclear who had ever truly held it. Two stars then, and two different ways the ground can shift beneath a number we thought was solid. VY Canis Majoris taught us that a star can be hard to measure because it hides inside its own shed material, blurring its edge. UY Scuti taught us that a star can be hard to measure because everything depends on a distance, and distance is treacherous, and a better instrument can rewrite it overnight. Both lessons point to the same quiet truth, the one that sits at the center of tonight's whole story. The hardest thing in astronomy is not finding the largest star. It is knowing how far away anything truly is. And that difficulty has a name, and a place in the sky, and a reason it falls hardest on exactly the stars we most want to measure. That is where we go next. We have now watched two giants lose their crowns, not because they changed, but because the distances we assigned them changed beneath our feet. So it is worth stopping here, in the middle of the lineage, to sit with the thing that keeps causing all this trouble. Because underneath every story we have told tonight, and every story still to come, there is a single difficulty doing the quiet damage. It is the reason the numbers keep shifting. It is the reason the largest stars are the hardest to pin down. And it is, in the end, the real subject of this whole night, more than any one star could ever be. The difficulty is distance, not size, not brightness, not temperature. Distance, plain and simple, is the hardest honest measurement in all of astronomy. This can feel surprising at first, because distance seems like it should be the easy part. We are surrounded, in daily life, by ways of knowing how far away things are. Our two eyes judge depth automatically. We have tape measures and laser rangefinders, and the steady knowledge that the far wall of the room is a certain number of steps away. But all of those methods depend on being able to get near the thing, or to bounce something off it, or to see it from two angles wide enough apart to matter. The stars allow none of that. They are so unspeakably far away that the entire orbit of the Earth around the Sun, a circle nearly 300 million kilometers across, becomes a vanishingly tiny baseline from which to judge them. Measuring the distance to a star is like trying to gauge the depth of a canyon by shifting your head a fraction of a millimeter. The shifts we are reading are almost impossibly small. And here is why that single difficulty matters so enormously for the size of a star. Everything about a star's true scale flows from its distance, and it flows in a way that magnifies any error rather than softening it. Think back to how the chain works. We measure how bright a star appears in our sky, which is straightforward enough. But how bright it appears is not how bright it truly is. A faint-looking star might be a modest star nearby, or a tremendously luminous one far away. To turn apparent brightness into true brightness, you must know the distance, and the relationship is steep. A star's apparent brightness falls off with the square of its distance. Place a star twice as far away, and it looks 4 times fainter, which means run the other way. If you have underestimated a star's distance by half, you will have underestimated its true brightness 4-fold. And since the calculated size of the star follows from that true brightness, the error rides all the way through to the radius. A modest mistake in distance becomes a large mistake in size. That is precisely what we watched happen to UY Scuti. The distance was revised, and because the distance is the root of everything, the size did not adjust gently. It collapsed. The star itself never moved. Only the foundation under our estimate shifted, and the whole edifice resting on it shifted with it. So distance is hard, and distance is everything. Now add the cruelest part of the arrangement, the detail that turns a difficulty into something close to a conspiracy of circumstance. The very stars we most want to measure, the giant, rare, short-lived supergiants, tend to live in exactly the places that are hardest to see into. To understand why, picture our galaxy not from inside it, where we are trapped, but as it would look from far away and above. The Milky Way is a vast flat disk of several 100 billion stars, with graceful spiral arms winding outward from a bright central bulge. Massive stars, the kind that become supergiants, are born in the dense, gas-rich regions of those spiral arms and toward the crowded inner galaxy near the center. That is where the raw material gathers thickly enough to build stars dozens of times heavier than the Sun. But those same regions are packed not only with stars, but with enormous clouds of interstellar dust, the fine, sooty grains that drift between the stars in their billions. And from our vantage point, stuck inside the disk, looking outward along the plane of it toward those crowded inner regions, we are looking through the thickest possible curtain of that dust. The grains absorb starlight and scatter it. They dim everything behind them and redden it, stealing the blue light more readily than the red, the same way the setting sun turns orange as its light slants through more of our atmosphere. Along the central band of the galaxy, that dust grows so thick that it blots out the light of countless stars entirely. We simply cannot see them. They are there, shining, but their light never reaches us in any usable form. Astronomers have a name for this blotted-out band of sky, and it is a wonderfully honest one. They call it the zone of avoidance. For most of the history of astronomy, it was the region that surveys quietly skipped over, because there was so little to be seen there through the murk. It is the part of the sky our maps avoid, not because nothing is there, but because the dust hides what is. And it lies, of course, straight across the galactic plane, straight across the crowded inner galaxy, straight across the very regions where the largest stars are most likely to be found. Trying to read a star through all of that is, in a real sense, like trying to read a page of writing through a wet paper bag. You can tell something is there. You can make out a smudge, a shape, a hint of the letters. But the fine detail is lost in the haze. And of all the fine details that dust steals, distance is the one whose loss costs the most, because everything else about a star's true scale is built on top of it. This is the quiet thesis underneath everything tonight. Our map of the galaxy is not a finished, confident document. It is a beautiful collection of fragments, assembled from the regions we can see clearly, with great gaps and smudges where the dust forbids us a clean look. The brightest, nearest, least obscured stars we know well, but the rare giants, hidden in the crowded, dusty inner galaxy, come to us dimmed and reddened and uncertain. Their distance is soft, their size is therefore softer still. We are not measuring these stars badly out of carelessness. We are measuring them as well as anyone could, through a curtain that nature drew across them long before we ever looked. And so the humbling we keep encountering tonight is not a story of mistakes. It is a story of honest limits. Every revised crown, every halved star, every number that came with an asterisk, traces back to this. The most extreme objects in our galaxy sit in the places we can see least well, and the measurement they most depend upon is the one the dust degrades the most. When the numbers shift, it is usually because someone found a slightly better way to peer through the haze, and the universe, on the far side of it, was a little different than the smudge had suggested. This is the lens through which the rest of the night comes into focus. We are about to meet Stephenson 2-18 in earnest, and it sits deep in this very murk, far out in the dusty inner galaxy, near the heart of the zone of avoidance. Its distance is uncertain for exactly the reasons we have just walked through, which means its size, that staggering headline figure, rests on the very foundation we now know to be the softest of all. And the story of how astronomers found it and very nearly dismissed it, begins with a single strange entry in an old catalogue. Imagine for a moment the unglamorous heart of how astronomy actually gets done. Not the grand telescope on the mountaintop, not the dramatic discovery, but the long, patient labour that comes before any of it. Someone over years photographs patch after patch of the sky, develops the plates, and records what is on them. Star by star, they note positions and brightnesses and colours, building a catalogue, a great ledger of the heavens. Most of the entries will never be famous. They are simply the raw inventory of the sky, set down carefully so that someone someday might find what they need inside it. This is where almost every story in astronomy truly begins, in a list, in a number, in an entry written down and set aside. Our story begins in exactly that way, with an American astronomer named Charles Bruce Stephenson. In the latter part of the 20th century, Stephenson compiled catalogues of stars, and among the tools he worked with was the infrared. This matters, and it is worth pausing on, because of everything we said in the last section about dust. Visible light, the light our eyes are built for, is scattered and absorbed heavily by interstellar dust. But infrared light, with its longer wavelengths, slips through that dust far more easily. It passes through the murk that stops visible light cold. So to peer into the dusty inner galaxy, into the very zone of avoidance we have been talking about, infrared is the tool of choice. It is the wavelength that lets us see the stars the dust would otherwise hide. Working in the infrared, Stephenson catalogued, among many other things, a tight grouping of stars in the constellation Scutum. Out in that dusty inner region of the galaxy, the grouping was eventually recognized as a star cluster, a family of stars born together from the same cloud of gas, traveling together through the galaxy. It came to carry his name. Informally, astronomers call it Stephenson 2. More formally, it is sometimes designated RSGC2, where RSGC stands for Red Supergiant Cluster, and that name tells you immediately why this particular patch of sky turned out to be so remarkable. Because Stephenson 2 is not an ordinary cluster. It is one of the richest concentrations of red supergiants known anywhere in our galaxy. Tucked into that one small region are more than 24 of these aging, swollen, massive stars, all of them in the late chapters of their lives, all of them having arrived at that stage at roughly the same time. To find so many supergiants gathered in one place is genuinely rare. Massive stars are uncommon to begin with, and they live fast and die young, so to catch a whole crowd of them in their red giant old age, all at once, in a single cluster, is a remarkable piece of luck. Stephenson 2 is a kind of natural laboratory for studying these stars, a place where the universe has conveniently set out a sample of them side by side. And within that crowd of supergiants, catalogued among its more than 24 members, was the star that would eventually carry the designation Stephenson 2018, simply the 18th member in the list, an entry among entries. There was at first nothing to suggest it deserved any special attention beyond its siblings. Except for one thing, it was too bright. When astronomers began to study the members of the cluster, Stephenson 2-18 stood out in a way that did not sit comfortably. It was far more luminous than the other supergiants around it, brighter by a margin that was hard to explain if it was simply one more member of the family. And that excess brightness, rather than being thrilling, was a problem, because there is a perfectly ordinary explanation for a star that looks too bright to belong, and that explanation is that it does not belong at all. Here is the difficulty. When we look toward a distant cluster, we are looking down a long tunnel of space, and other stars, entirely unrelated to the cluster, can happen to lie along the same line of sight. A star much closer to us, sitting in the foreground between us and the cluster, would appear in roughly the same direction in the sky. It would look as though it were part of the group, but being far nearer, it would also look far brighter than the genuine cluster members, simply because it is closer. So a suspiciously bright star in a cluster is exactly what you would expect from a foreground interloper, a nearby star that merely photobombs the family portrait, lining up by chance in front of the real cluster behind it. That was the natural suspicion about Stephenson 2-18. Perhaps it was not a true member of the cluster at all. Perhaps it was simply a nearer star, ordinary in itself, that happened to fall along the same direction in our crowded, dusty view of Scutum, and only seemed to belong. If that were the case, then its brightness would mean nothing special. A nearby star looking bright is no mystery. Only if it truly sat at the cluster's great distance and still shone that brilliantly, would the brightness become extraordinary, because then it would mean the star was pouring out a genuinely staggering amount of light. And so, faced with this ambiguity, astronomers did the reasonable thing. They set the question aside. With so suspicious a brightness, and no easy way to resolve whether it was a true member or a foreground imposter, Stephenson 2-18 became an awkward case, a flagged anomaly, the kind of object you note and then move past while you study the cleaner, more cooperative stars around it. The cluster had more than 24 members that behaved sensibly. There was plenty to work on without wrestling with the one that did not fit. So the strange, too bright entry waited, its true nature unresolved, neither confirmed as a giant, nor dismissed as an interloper. Just a question mark in the ledger. It is worth sitting with how quiet this is, because it runs against the way we usually imagine discovery. There was no dramatic moment, no astronomer crying out at the eyepiece. The largest, or very nearly the largest, star we have ever measured spent a stretch of time as little more than a footnote, a number flagged as not quite making sense, deliberately left to the side. Its enormity was not hidden in some far unreachable corner of the cosmos. It was right there in the catalogue the whole time, recorded, numbered, available to anyone who looked. What was missing was not the data. What was missing was the one measurement that could settle whether the star truly lived at the cluster's distance, or merely seemed to. And that, in the end, is how the largest stars tend to come to us, not with a flourish, but with a question that sits unanswered for a while. We met this same shape earlier tonight. UY Scuti logged in 1860 and left alone for a century and a half. VY Canis Majoris, wrapped in ambiguity about where it even ended. And now Stephenson 2-18, too bright to make easy sense, parked in the cluster's records with a quiet asterisk beside it, waiting for someone to ask the right question in the right way. The right question, it turned out, was not about brightness at all. Brightness was the thing causing all the trouble. The way to settle whether Stephenson 2-18 belonged to the cluster was to stop looking at how bright it was, and to look instead at how it moved. Every star in a true cluster travels together, sharing a common motion through the galaxy, drifting in the same direction at the same speed, like a flock of birds holding formation. A foreground imposter would not share that motion. It would be going its own way, at its own pace, betraying itself as an outsider. So the question became a question of motion, and there is a way, an elegant and beautiful way, to measure how a star is moving toward us or away from us, even across 19,000 light-years of dusty space, using nothing but the light it sends us and the careful reading of the colors hidden inside it. That measurement, And what it finally revealed is where we go next. The light from a star carries more than warmth and color. Spread it out carefully, the way a prism splits sunlight into a rainbow, and you find that the smooth band of color is crossed by fine dark lines, like a barcode printed across the spectrum. Those lines are fingerprints. Each one marks a particular element in the star's outer layers: hydrogen, calcium, iron, each soaking up light at its own precise wavelengths, always in the same places, as reliable as a signature. Read those lines, and you can tell what a star is made of from across the galaxy, without ever touching it. That is one of the quiet miracles of astronomy. But the lines do something else, something even more useful for the question we left hanging at the end of the last section. They move, not on the star, but in the spectrum we receive. If a star is traveling toward us, the lines in its light all shift slightly toward the blue end of the spectrum. If it is traveling away from us, they shift toward the red. It is the same effect you hear when an ambulance passes, its siren rising in pitch as it approaches and dropping as it recedes. Light behaves in a parallel way. Motion toward us crowds the waves a little closer. Motion away stretches them a little longer. And the whole barcode of dark lines slides one way or the other by an amount that tells you exactly how fast the star is moving along our line of sight. Astronomers call that speed the star's radial velocity, the part of its motion directed toward us or away. And radial velocity was the key that finally unlocked Stephenson 2.2.18. Recall the question: was this too bright star a true member of the Stephenson 2 cluster, sitting at its great distance and therefore genuinely enormous? Or was it a nearer foreground star, ordinary in itself, only pretending to belong? Brightness could not settle it, because brightness was the very thing in dispute. But motion could. A true member of the cluster would share the cluster's motion through the galaxy. All the stars born together from one cloud drift together afterward, carried along on the same broad current, moving toward or away from us at very nearly the same speed. A foreground imposter, born somewhere else entirely, would be going its own way at its own pace. Measure how fast Stephenson 2-18 was moving along our line of sight, compare it to the rest of the cluster, and the answer would reveal itself. So astronomers measured it. They took the star's spectrum, found those dark fingerprint lines, measured how far they had shifted, and read off its radial velocity. Then they compared that figure to the radial velocities of the other confirmed cluster members, the ones whose membership was not in doubt. It matched. Stephenson 2-18 was moving with the cluster, drifting at the same pace as its siblings. It was not a foreground imposter. It was a true member, sitting at the cluster's full distance, somewhere around 19,000 light-years away. And that result changed everything, because it meant the brightness was real. The star was not bright because it was close. It was bright because, at that tremendous distance, it was genuinely pouring out an extraordinary flood of light. The anomaly was no longer a problem to be set aside. It was a measurement to be taken seriously. With membership settled, the rest of the calculation could proceed, and it followed the same chain we have seen all night. Begin with the distance, now confirmed at the cluster's value. Combine that distance with how bright the star appears, and you recover its true luminosity, the full amount of light it actually radiates. The figure that emerged was staggering, a luminosity of something like 440,000 times that of the Sun. Then bring in temperature, the star's spectral type, the overall character of its light, marks it as a cool red supergiant, with a surface temperature down around 3,000 degrees, far cooler than the Sun's surface. And now the two facts press against each other in a way that forces the conclusion. Here is a star that is cool, its surface dim per unit of area, glowing only the soft red of low temperature. And yet it is pouring out nearly 500,000 times the sun's light in total. There is only one way for something cool to be that luminous. It must be vast. A dim surface can still outshine almost anything if there is simply enough of that surface. The light a star gives off depends on how hot each patch of its surface is, and on how much surface there is altogether. If each patch is faint, the only way to reach an enormous total is to have an enormous area, which means an enormous radius. Run that relationship through with Stephenson 2-18's luminosity and temperature, and the radius that comes out is the number we open the night with. Roughly 2,150 times the radius of the sun. There it is, the headline figure, derived not from a single dramatic measurement, but from this patient chain, a distance confirmed by matching motions, a luminosity drawn from that distance and the apparent brightness, a temperature read from the color of the light, and a radius that follows, by simple and unavoidable physics, from putting them together. And in the same breath that we arrive at that number, we have to set it back down gently in everything we have learned tonight, because the chain that produced it is exactly the chain we spent the last several sections learning to distrust. Every link in it depends on the distance, and the distance, out here in the dust-choked inner galaxy near the heart of the zone of avoidance, carries an uncertainty of more than 50%. That is not a small wobble. It is a genuinely wide range. The 2,150 figure is best understood not as a settled fact, but as the high end of a contested span, with careful estimates running roughly from 1900 to perhaps 2400 solar radii, depending on the assumptions you make. And underneath even that range sits the membership question, which the radial velocity addressed, but did not silence forever. Some astronomers have continued to wonder, in the years since, whether the star's unusual properties might still hint at something not quite ordinary about its place in the cluster. So we hold both things at once, which is the whole discipline of this story. Stephenson 2-18 is, by its most quoted figure, around 2,150 times the radius of the Sun, one of the largest stars ever measured. And that figure rests on a distance we are more than half uncertain of, derived through the haze of the dustiest part of the galaxy, by the very chain of inference that has humbled every giant before it. The number is real, the doubt is real. They belong together, and an honest telling keeps them together, the way the careful astronomers who measured the star have always done. But let us not let the uncertainty rob us of the wonder, because even at the low end of that contested range, even at 1900 solar radii, rather than 2100, we are still talking about a star of almost incomprehensible size. The doubt changes the last digits. It does not change the staggering fact underneath them. Whatever its exact figure, this is a star so large that the words we use for ordinary bigness simply fall away. And the only honest response is to slow down and try, gently, to picture it. So that is what we will do next. We will take that radius, whatever its precise value, and walk it outward through our own familiar solar system, one planet at a time, until we feel, as nearly as a mind can, just how far this single star would reach. Let us begin where every sense of scale should begin, with something you already know, the sun. It hangs in our sky as a small bright disk, no wider to the eye than the full moon, and it is easy, because of that, to think of it as a modest thing. It is not. The sun's radius is about 696,000 kilometers. To put that in terms of the world under your feet, You could line up 109 Earths side by side across the face of the Sun, and they would just span it. Pour Earths into its volume rather than lining them up, and you would need well over 1 million of them to fill it. The Sun is not a small bright disk. It is a vast furnace 9/10 of a million kilometers across, and everything we have ever known has unfolded in orbit around it. Hold that Sun in your mind, the real one, the enormous one. Now we are going to multiply it. Stephenson 2/18, at its often quoted radius, is about 2,150 times wider than that. So take the Sun, already large beyond easy picturing, and grow it more than 2,000-fold in every direction. Its radius would no longer be 696,000 kilometers. It would be something close to 1.5 billion kilometers. From the center of the star out to its faint edge would be a journey of 1.5 billion kilometers, which means straight across, edge to edge, the star would span roughly 3 billion kilometers. These numbers are too large to feel, so let us stop counting and start walking. Place Stephenson 2/18 where our Sun is, its center sitting exactly where the Sun's center sits. Now stand at that center and walk outward, and let us see what the star swallows on the way. First thing we reach is Mercury, the innermost planet, scorched and small, circling at about 58 million kilometers from the Sun. We are barely out of the door. The star's surface is more than 25 times farther out than Mercury's orbit. Mercury is not merely inside this star. It is lost near the very center of it, a tiny cinder adrift deep in the star's core regions. Keep walking. Venus, at 108 million kilometers, the brilliant evening star, the planet most like Earth in size, also gone, also deep inside, also nowhere near the edge. Now we come to a place that should make us pause, because it is home. Earth orbits the Sun at about 150 million kilometers. That distance, the gap between us and our own star, is so large that sunlight, moving at the fastest speed there is, takes 8 minutes to cross it. It is the span that defines our entire experience of warmth and seasons and day and night. And the surface of Stephenson 2/18 would lie about 10 times farther out than that. Our whole orbit, the great circle that carries us through every year of our lives, would fit inside this star roughly 10 times over, nested deep within it like a small ring dropped into a vast bowl. The Earth would not be at the edge of this star. It would be buried in its interior, with the true surface still a tremendous distance beyond. We are still walking, and we have not yet reached the edge. Mars next, the red planet, at about 228 million kilometers swallowed. Then we cross into the asteroid belt, that broad scattered ring of rock and rubble between Mars and Jupiter, its main concentration sitting a few 100 million kilometers out. Gone, all of it, inside the star. And still the surface is not here. Still we walk. Then comes Jupiter, and Jupiter is not a small world. It is the king of the planets, a giant in its own right, more massive than all the other planets combined, orbiting at about 778 million kilometers from the Sun. If you have ever seen Jupiter through even a small telescope, with its stripes and its 4 bright moons strung out beside it, you know it does not feel like a thing that could simply be lost inside something larger. And yet here it is swallowed too. Jupiter's whole orbit, vast as it is, sits comfortably inside Stephenson 2/18 with room to spare. We pass it and we keep walking, because even now we are not quite at the edge. The edge, when we finally reach it, lands almost exactly at the orbit of Saturn. Saturn, the ring planet, the jewel of the solar system, circles the Sun at around 1.5 billion kilometers, and that is near enough, where the faint outer reaches of Stephenson 2-18 come to rest. Stand on the surface of this star, if it had anything you could stand on, and look outward, and you would be gazing across the gap toward where Saturn glides through the dark. Everything inside Saturn's orbit, the entire inner and middle solar system, every world we have ever visited, every planet you can name without effort, all of it would lie within this single star, with only the cold outer planets, Uranus and Neptune, left orbiting somewhere out beyond its edge in the dark. One star, reaching from where the Sun sits all the way out to Saturn. Not a system of objects, one object. And we have only spoken of how far across it is. There is a second number, hiding behind the first, that is in some ways even harder to hold. Volume does not grow in step with width. When you make something twice as wide, you do not double its volume, you increase it eightfold, because volume grows with the cube of the radius. And Stephenson 2-18 is not twice as wide as the Sun. It is more than 2,000 times wider. Cube that, and you arrive at the number we began the night with. You could pour something close to 10 billion suns into the volume of this single star. Not 10 suns, not 10,000, not 10 million, 10 billion. Take our entire enormous Sun, the furnace that holds the whole solar system in its grip, and you would need 10 billion of them packed together to fill the space this one star occupies. Now let us trade these unimaginable quantities for two slow, almost dreamlike images, the kind you can actually carry into sleep. Imagine an ordinary airliner, the sort that crosses an ocean, cruising along at its usual speed of perhaps 900 kilometers an hour. Set it to fly not across the Earth, but around Stephenson 2-18, a single lap around the star's circumference, and let it never stop, never refuel, never rest. How long would that journey take? Roughly 1100 years. If a flight had departed on its loop around this star in the early medieval period, when much of Europe was still a patchwork of small kingdoms and the great cathedrals had not yet been built, that flight would only now, in our own century, be completing its single circle. 1100 years of continuous flight, just to go around once. And here is the last image, the one I find quietest of all. Light itself, the fastest thing in the universe, travels around the Sun's circumference in about 14.5 seconds. A beam of light could circle our entire Sun in less time than it takes to read this sentence aloud. Now send that same beam around Stephenson 2-18. It would take more than 8 hours. Light, which crosses from the Sun to the Earth in 8 minutes, which could lap our Sun more than 200 times in a single minute, would need 8 full hours, the length of a night's sleep, to make one circuit of this star. You could close your eyes as that beam set out, fall asleep, pass through your dreams, and wake in the morning, and the light would only just be finishing its lap. That is the size of it. A star you could walk outward through, past Mercury and Venus, and Earth and Mars and the asteroids and Jupiter, and still not reach the edge until Saturn. A star that would hold 10 billion suns. A star so large that light needs a whole night to go around it once. And here is the gentle turn, the thing this whole night keeps circling back toward. As staggering as all of this is, the size is not even the strangest thing about Stephenson 2-18. There is something about what this star is made of, or rather how little of anything it truly is, that is stranger still. For all its reach out to Saturn, for all its 10 billion suns of volume, this star is, in a sense we will explore next, barely there at all. That is where we go, into the soft and almost ghostly heart of what this star really is. Picture for a moment that we could do the impossible. Imagine a small spacecraft, sturdy and well shielded, flying in from the dark toward the outer edge of Stephenson 2-18. It is approaching the surface of a star, the most violent and dense kind of object we know, and so you might brace, the way you would brace before plunging into deep water. You might expect a wall, a sudden boundary, a sheet of fire, a moment where the ship crosses from empty space into the searing substance of the star and is, in an instant, overwhelmed. That moment never comes. There is no wall. Instead, the ship would drift into a region where space is no longer quite empty, where a faint, warm haze begins to thicken around it, so gently that you could not name the exact instant you arrived. It would press deeper, and the haze would grow slowly less faint, slowly warmer, a thinning then thickening fog with no edge to it anywhere. The ship would be inside the star by any reasonable definition, and yet it would feel almost nothing. A warmth, a whisper of gas against the hull, not a wall, not a plunge, but a slow dissolving of the dark into something barely more than dark. You could fly a long way into this star before anything happened that you would call dramatic at all. That is the strangeness underneath the size, because Stephenson 2-18, for all its reach out to Saturn, for all its 10 billion suns of volume, is made of almost nothing. It is, in the most literal sense, one of the emptiest things in the universe. Here is how that can be true. We have spent the night marveling at the star's size, its volume, the sheer amount of space it fills. But volume is only half of what makes a thing substantial. The other half is mass, the actual quantity of matter present. And here is where Stephenson 2-18 turns out to hold a quiet contradiction at its heart. Its volume is 10 billion times the sun's, but its mass is not. Its mass is only somewhere around 12 to 15 times the mass of the sun. 12 to 15, not 10 billion, not 10,000. A mere dozen or so suns worth of material, spread out across a volume that could hold 10 billion of them. Take a moment to feel the gap between those two numbers, because the whole wonder of this section lives inside it. 10 billion units of room, a dozen units of stuff. The matter that makes up this star has been spread so impossibly thin across so impossibly vast a space that what results is a density almost beyond belief. Work it through, and the average density of Stephenson 2-18 comes out to something around 1/1,000,000th of a gram per cubic centimeter. To feel what that means, compare it to the sun, which is itself a ball of gas, not a solid thing. The sun's average density is about 1.5 grams per cubic centimeter, a little denser than water. Stephenson 2-18 is roughly 100 million times thinner than that, 100 million times less dense than our already gaseous sun. And we can go further, because that comparison still does not quite land. Think about the best vacuum that human beings can create. In the finest laboratory vacuum chambers on Earth, where scientists pump out the air to study the most delicate experiments, the emptiness achieved is extraordinary, far emptier than anything in your daily life. And the outer layers of Stephenson 2-18 are, in places, thinner than that. The gas in the great swollen envelope of this star is more rarefied than the best vacuum we know how to make. We build elaborate machines to chase that kind of emptiness here on Earth, and a red supergiant achieves it casually, across a volume the size of a solar system, simply by being what it is. So when you imagine this star, set aside the picture of a solid glowing ball. That picture belongs to the sun, and even there it is not quite right, but it is at least useful. For Stephenson 2-18, it fails completely. This is not a ball. It is a cloud, an enormous, faintly glowing, warm cloud of gas, thinning out toward its edges into something close to vacuum, with a small, dense, fiercely burning core buried far down at the center, a fusing heart wrapped in a fog the size of the inner solar system. That is the truer image. Not a sphere of fire, but a hot point lost inside an immense and tenuous haze. Which brings us back to the question the size alone never answers. Where does this star end? For the Sun, we had an answer. The photosphere, that layer where the gas finally thins enough to let light escape freely, gives the Sun a reasonably crisp edge, a surface we can point to and measure. But for a star like this, the gas thins so gradually across such an enormous span that no single layer stands out as the true boundary. There is no place where you could honestly say, here, exactly here, the star stops and space begins. The transition is a gradient, a slow fading from faint glowing plasma to fainter plasma to the thinnest wisp, and finally, somewhere imperceptibly, to the dark between the stars. The edge is not a line. It is a long, soft blur. And this is why the very radius we have been quoting all night, that staggering 2,150 solar radii, becomes, in the end, partly a matter of definition. The number is not wrong, but it depends on a choice, a decision about which faint layer of the fog we agree to call the surface. Choose a slightly deeper layer and the star is a little smaller. Choose a slightly more tenuous outer layer and it is a little larger. The star itself makes no such distinction. It simply fades outward the way mist fades, with no firm declaration of where it ends. We draw the line for our own convenience so that we can write a number down. The star does not honor the line. It does not have one. There is something genuinely beautiful in this, and worth letting settle as the night deepens. We started with a question that sounded simple, almost crude. How big is the biggest star? And the further in we have gone, the more that question has softened in our hands, until here, at the heart of it, we find that the star does not even have a definite edge to measure. The biggest star is not a hard-walled giant looming in the dark. It is a vast, gentle, glowing haze, denser than empty space but far thinner than air, holding a small hot heart at its center and trailing off into the dark at its edges with no clear place to say goodbye. You could fly into it and barely know. You could be inside it and feel only a warm fog. The thing we call the largest star is, in a real sense, more absence than presence, more cloud than star, more a slow brightening of the dark than an object with a skin. And if it is held together so loosely, so faintly, by gravity grown weak across all that distance, then a new and gentle question follows naturally. What keeps a thing like this together at all? If its outer layers are thinner than a laboratory vacuum, barely tethered to the core so far below, what stops them from simply drifting away into space? The answer, it turns out, is that to some extent, nothing does. This star is quietly, continually letting go of itself, shedding its outermost fog into the dark, not in some crisis or catastrophe, but as a slow and ongoing way of being. That gentle, perpetual letting go is where we turn next. We use the phrase so easily, held together, that we rarely stop to ask what it really means for a star. For most of the objects in our lives, holding together is simple. A stone holds together because the bonds between its atoms are strong, locking it into a fixed shape that resists almost anything. A planet holds together because its gravity is firm enough to keep its rock and metal pressed into a ball. These things have a definite skin, a clear inside and outside, a shape they keep. but a star like Stephenson 2 to 18 holds together in a far looser and more provisional way, and at its outermost reaches, the honest truth is that it barely holds together at all. The gravity a star exerts at its surface depends on two things: how much mass it has, and how spread out that mass is. Pile the mass up small and tight, and the surface gravity is fierce. Spread the same mass across a vastly larger sphere, and the surface gravity grows faint, because the outer layers sit so far from the center that the pull reaching them has thinned almost to nothing. Stephenson 2 to 18 has only a dozen or so suns worth of mass, and it has spread that mass across a sphere reaching out towards Saturn. The result, at its outer edge, is gravity grown astonishingly weak. The gas drifting in the star's outermost regions is held by a pull so faint that it would feel, to that gas, almost like floating free. It is bound to the star in the way a thin morning mist is bound to a hillside, present for now, clinging loosely, but with nothing firm holding it down. The slightest push would be enough to carry it away. And there is always a push. The light streaming out from the star's hot core, that ceaseless river of radiation we have talked about all night, presses outward on every layer of gas it passes through. Down near the dense core, that push is just one force among many, balanced and contained. But out at the tenuous edge, where gravity has faded almost to nothing, the gentle pressure of the starlight is enough to win. It nudges the outermost gas outward, lifts it free of the star's faint grip, and carries it off into space. And so the star bleeds. Continuously, quietly, layer by layer, it loses its outermost material into the dark. This is what astronomers call mass loss, and in a red supergiant it is not a rare event or a sign of trouble. It is a way of life. Stephenson 2 to 18 is wrapped in a steady outflowing wind of its own substance, a slow exhalation of gas, and further out where things have cooled, of dust drifting away from the star in all directions. It is forever shedding pieces of itself, forever letting its outer fog disperse into the surrounding galaxy. The star you see is not a sealed and finished object. It is something more like a fountain, constantly losing its outermost water, even as the shape of the fountain endures. It is worth resisting the urge to hear this as something violent or dying. The language we reach for when a thing loses material tends toward alarm. Words like bleeding and shedding and wasting away. But there is nothing frantic about this. It is slow, and it is gentle, and it is simply what these enormous, loosely held stars do. A red supergiant losing mass is not a star tearing itself apart in a crisis. It is a star so large and so softly bound that its own faint light is enough to coax its outer layers, little by little, back out into the space they came from. Picture not an explosion, but an exhalation. A long, slow breathing out that goes on for many thousands of years. And there is something quietly generous in it too, if you let yourself see it that way. The material the star releases does not vanish. It drifts out into the galaxy and becomes part of the great reservoir of gas and dust from which new stars and new worlds are eventually made. The star is returning its substance to the place it was borrowed from, enriching the space around it, sowing the raw material of future things. We will come back to that thought near the end of the night, because it reaches, in a surprising way, all the way down to you. For now, it is enough to notice that the star's losing of itself is also a kind of giving. This perpetual mass loss also deepens the mystery of the edge we sat with in the last section. We already saw that the star has no sharp surface, that it fades outward into a gradient with no clear boundary. Now add this constant outflowing wind, and the picture grows softer still. There is the faint glowing fog of the star's outer envelope. Then there is the wind streaming away from it, gas that was the star a little while ago and is now departing. Then there is the slowly expanding shell of material it has shed over the centuries, drifting ever outward. Where, in all of that, does the star end and the galaxy begin? The question has no clean answer, because the star does not end so much as gradually become its surroundings. It trails off into the space around it, the way a scent trails off into a room, present and then fainter and then simply gone, with no line you could ever draw between here and there. This is the same idea we first met all the way back when we watched ordinary stars swell into supergiants. The idea that such a star becomes more cloud than sphere. We can now see how completely true that is. Stephenson 2-18 is not a sphere with a fuzzy edge. It is a fusing core, wrapped in a vast tenuous fog, wrapped in turn in an outflowing wind, wrapped in turn in the slowly dispersing memory of everything it has already let go. It is less an object than a process, less a thing than an ongoing event, a slow fountain of starlight and gas playing out across a volume the size of the inner solar system and across stretches of time longer than our whole recorded history. And yet, for all this gentleness, there is a real puzzle buried in it, one we have circled around several times tonight without quite landing on. If this star is so loosely held, if its own light is enough to lift its outer layers away, then by the simplest accounting of the forces at play, it should be losing itself far faster than it does. By the cleanest version of the physics, the version drawn for tidy, uniform stars, a star this large and this luminous sites right at the edge of being unable to hold itself together as a coherent star at all. This is the heart of the phrase in our title, the sense in which Stephenson 2-18 is a star that, by our simplest equations, should not quite be able to exist. It does exist. It is out there right now, holding its loose shape, shedding gently but enduring. So the simplest equations must be missing something, and what they are missing turns out to be one of the loveliest pieces of physics in this whole story. 100-year-old idea about light and gravity, and the way that real stars, clumpy and porous as they are, slip past a limit that idealized ones cannot. That limit, and the man who first wrote it down, are where we go next. Early in the 20th century, an English astronomer named Arthur Eddington spent a great deal of his life thinking about what holds a star together, and in doing so, he wrote down one of the most quietly important ideas in all of stellar physics. It begins with the same tension we have returned to again and again tonight, the contest between gravity pulling a star inward and the pressure of its own light pushing outward. Eddington realized that this contest has a ceiling. There is a brightness beyond which a star cannot calmly shine, because past that point, the outward push of its own radiation overwhelms the inward grip of its gravity, and the star can no longer hold its outer layers in place. The idea is gentler than it sounds, and you can feel it without any mathematics. A star's gravity tries to hold its gas in. A star's light pushes that gas out. For a dim star, the light's push is feeble, and gravity wins easily, and the star is stable. But the brighter a star becomes, the harder its light pushes. Crank the brightness up, and eventually you reach a point where the outward shove of the radiation exactly equals the inward pull of gravity. That balance point is what we now call the Eddington limit, the maximum brightness at which a star of a given mass can still keep hold of itself. Shine any brighter than that, and your own light begins to drive your outer layers off into space faster than gravity can hold them down. This is not a small or obscure idea. It governs how the most massive, most luminous stars in the universe can exist at all, setting a natural cap on how bright a star of a given mass is allowed to be. And crucially, the limit depends on mass. A heavier star with stronger gravity can shine more brightly before reaching its limit. A lighter star reaches its ceiling sooner. So to ask whether a particular star is near its Eddington limit, you need two numbers, its mass and its luminosity, and you compare them. Now bring Stephenson 2-18 to that comparison. Recall the two numbers. The star's mass is modest, only somewhere around 12 to 15 times the Sun's. Its luminosity, though, is enormous, somewhere near 440,000 times the Sun's. Work out the Eddington limit for a star of 12 to 15 solar masses. The brightest it should be able to shine while still holding itself together, and you get a figure of roughly 300,000 to 320,000 times the Sun's luminosity. And there is the problem, laid bare. The limit says about 300,000. The star is shining at about 440,000. Stephenson 2-18 is pouring out meaningfully more light than its own gravity should be able to contain. By the straightforward reading of Eddington's idea, this is a contradiction. A star shining above its Eddington limit should not be able to hold its outer envelope at all. The radiation should be winning. The star should be driving itself apart, shedding its outer layers so rapidly that it could not persist in the form we observe. By the simplest version of the physics, a star with this mass and this brightness should not be sitting calmly out in Scutum as a coherent supergiant. It should not, in that precise and limited sense, exist. And there is the phrase from our title, finally arrived at in full, a star that shouldn't exist. Now we can say exactly what it means, and exactly what it does not mean. It does not mean that physics is broken, or that the universe has produced something impossible, or that we should be alarmed. It means something far more modest and far more interesting. It means that this star sits on the wrong side of a line drawn by our simplest equations, and that fact is not a crisis for the star. It is a clue for us. It is the universe gently informing us that the simple equations were leaving something out. So what were they leaving out? This is where the resolution arrives, and it is genuinely lovely. Eddington's limit, in its clean classical form, rests on the same kind of assumption we met when we talked about the theoretical ceiling on stellar size. The star is smooth, uniform, a perfect sphere of evenly distributed gas, the same in every direction, with light pressing outward evenly through it, like water rising evenly through sand. Under that assumption, the radiation has nowhere special to go. It pushes on all the gas equally, and once it pushes hard enough, all the gas goes. The limit is sharp because the star is imagined as perfectly even. But real supergiants are nothing like that. We have spent this whole movement learning just how unlike that they are. Stephenson 2-18 is not a smooth uniform sphere. It is a roiling, turbulent, deeply uneven thing, with vast convective cells churning gas up from below, with denser clumps and thinner gaps threaded all through its enormous envelope. It is porous and patchy and irregular, more like a shifting foam than a still pond. And that messiness changes everything about how the radiation escapes. In a clumpy, porous star, the light does not have to push uniformly against every parcel of gas. It can find the gaps. It threads its way out through the thinner, lower density channels between the denser clumps, leaking outward along paths of least resistance, the way water finds the cracks in a pile of stones, rather than lifting the whole pile at once. The radiation escapes without having to lift the entire envelope. because it is not pressing evenly on a uniform shell. It is slipping through the porous structure of a foam, and so the star can shine above its naive Eddington limit and still, somehow, hold most of itself together. The light leaks out through the gaps instead of blowing the whole star apart. Astronomers have a name for stars in this state, shining above the simple limit yet enduring. They call them super Eddington, and they are real. We know of others. Stephenson 2/18 is not a lone impossibility, but a member of a small, strange family of stars that live above the classical line precisely because they are too messy for the classical line to apply to them cleanly. The clumpy structure that makes them so hard to model is exactly the structure that lets them survive. So the resolution of our title is this, and it is worth saying plainly and gently just once. Shouldn't exist is what the simplest equation says. When you feed it a tidy, uniform, imaginary star. The truer statement is that the equation was drawn for neater stars than this one. Stephenson 2/18 does exist, calmly, out in the dust of Scutum. And the fact that our cleanest formula says it cannot is not a failure of the star. It is an invitation to write a better formula. The physics of these extreme stars, the porous winds, the clumpy envelopes, the way radiation and gas negotiate their slow escape, is honestly not fully understood even now. There are open questions here that working astronomers are still patiently chipping away at. And Stephenson 2/18, sitting serenely above a limit it is not supposed to be able to exceed, is one of the very reasons those questions stay open and alive. There is something restful in that, I think, as a place to rest the mind tonight. We drew a clean line, and the universe placed something just beyond it, not as a rebuke, but as a quiet reminder that our lines are drawn for our own convenience, and the universe is under no obligation to honor them. The star is not breaking a rule. It is showing us that the rule, in its simplest form, was always an approximation, and that the real thing is messier and more forgiving and more beautiful than the approximation allowed. We have now seen what this star is, how vast, how tenuous, how gently it holds itself above the limits we imagine for it. What remains is to ask where it is going, because a star like this is not only enormous and strange, it is also old, and its story is moving slowly toward an ending. That ending is where we turn next. Every star is in the end a story about fuel. It lives for as long as it has something to burn, and it changes its character each time it runs out of one fuel and is forced by gravity to find another. We watched the first chapter of this story much earlier tonight, when an ordinary star exhausts the hydrogen in its core and swells into a red giant. For a star as massive as Stephenson 2/18, that was only the beginning. A star this heavy has the gravity, and therefore the inner heat and pressure, to push much further down a long ladder of fuels than a modest star like the Sun ever could. And following that ladder, rung by rung, leads to one of the most elegant and inevitable endings in all of nature. It works like this. When the core's hydrogen is spent, fused into helium, the core contracts under gravity and heats up, as we have seen. But in a star this massive, the contraction does not simply stall there. The core grows hot enough, tens of millions of degrees and beyond, to do something new. It begins to fuse the helium itself, welding helium nuclei together into carbon and oxygen. A new fuel, a new fire, a new source of outward push to hold gravity off a while longer. But helium too runs out, and again the core contracts, and again it heats, and again, because the star is so massive, it crosses a new threshold and a new fuel ignites. The carbon begins to fuse. When the carbon is spent, neon. When the neon is spent, oxygen. Each fuel, when exhausted, leaves behind an ash that becomes the next fuel, and each new burning requires a higher temperature than the last, reached only because gravity keeps squeezing the spent core hotter and tighter. The star climbs the ladder of the elements, hydrogen to helium to carbon to neon to oxygen to silicon, each rung burning faster and fiercer than the one before. And here the timescales become almost startling. The hydrogen burning phase of a massive star lasts millions of years, but each successive fuel burns more quickly, because each releases less energy, and the star is consuming it ever more voraciously to hold itself up. Helium burning lasts perhaps a few 100,000 years. Carbon, a few hundred years. The later stages collapse to almost nothing in stellar terms. By the time the star reaches the burning of silicon, the final rung, the whole phase may last only a day or so. A star that has shone for millions of years races through its last fuel in an afternoon. There is no need to feel any alarm in this. It is simply the long story reaching its final pages, the pace quickening the way a story does as it nears its close. Through all of this, the star takes on a remarkable inner structure. Because each fuel burns in its own layer, at its own depth and temperature, the star arranges itself into concentric shells, like the layers of an onion. Hydrogen still fusing in a thin shell near the surface. Below it, a shell of helium burning. Below that, carbon, then neon, then oxygen, then silicon, each in its own layer, each hotter and denser than the one above. And at the very center, where the silicon burning leaves its ash, something gathers that will bring the whole long story to its end. Iron. Iron is where the ladder stops, and the reason is one of the most quietly fundamental facts in all of physics. All the fusion we have described, every rung of the ladder, releases energy. That is the whole point of it, the source of the outward push that holds the star up against its own gravity. Fuse light elements into heavier ones, and a little energy comes out, and that energy is the star's life. But this generosity does not continue forever. As you fuse your way up toward heavier and heavier elements, the amount of energy each fusion releases grows smaller until you reach iron. And iron is special. Iron is the most tightly bound nucleus there is, sitting at the very bottom of a kind of energy valley. To fuse iron into anything heavier does not release energy. It absorbs it. Fusing iron costs the star energy rather than giving it any. Consider what that means for a star that has lived its entire existence by the outward push of fusion. When the core finally fills with iron, the fire that has held the star up for all those millions of years cannot continue. There is no next rung. There is no fuel beyond iron that will give back more than it takes. The core can fuse no further, and so the outward push, the pressure that has balanced gravity since the star was born, simply fails. Gravity, which has been patient this whole time, waiting at the door through every chapter, finally has nothing left to push against it. And then it happens very quickly. With the outward pressure gone, the iron core, by now larger than the sun, yet packed into a ball, perhaps the size of a city, collapses under its own gravity in a fraction of a second. Not over years, not over days, but in an instant, the core falls inward, crushing down to almost unimaginable density. The collapse is so sudden and so violent that the infalling material rebounds, slamming into the now ultra-dense core and bouncing back outward in a shockwave of catastrophic force. That rebounding shock, helped along by an outpouring of ghostly particles called neutrinos streaming up from the collapsed core, races outward through all those carefully layered shells and blows the entire outer star apart. This is a supernova, the death of a massive star announced across the galaxy in a flash of light that can, for a few weeks, outshine billions of ordinary stars combined. This is the ending that waits for Stephenson 2-18. It is, in the language of stellar life, very near the close of its story. It has long since left its hydrogen-burning youth. It is an aged, swollen supergiant, fusing heavier elements in a deeply layered core, climbing the last rungs of the ladder toward the iron that will end it. We cannot say precisely how near the end it stands, because the final stages, fast as they are in stellar terms, still unfold over timescales far longer than any human watch. But the direction of the story is not in doubt. A star this massive ends in collapse, and collapse in a supernova. The iron is gathering, or will gather, at its heart, and when the fire can climb no higher, gravity will have its moment. There is no need to read any of this as grim. A supernova is not a tragedy in the way a human ending can be. It is the natural and necessary final chapter of a massive star's life, and it is, as we will see in a moment, one of the most creative events the universe knows how to perform. The collapse that ends the star is also the forge in which much of the matter we are made of was first created. The ending is not only an ending, but that thread we will pick up shortly. For now, hold the quiet shape of it. A star that has lived for millions of years by climbing a ladder of fires, arriving at last at the one rung it cannot climb, and falling in a single second into the brilliant ending that all stars this large are bound for. It is a long story reaching its final page, calmly, inevitably, the way all such stories do. And when that page finally turns, the light of it will set out across 19,000 light-years of darkness to reach us. What that arrival might look like, and the strange, gentle truth folded into the distance, is where we turn next. When Stephenson 2-18 finally reaches its ending, when the iron gathers and the core falls, and the star tears itself apart in a supernova, that ending will not stay private. The light of it will leave the star and begin a long journey across the galaxy, and some of that light will be pointed, by chance, in our direction. So it is worth asking, gently, what that arrival might look like from here, from a quiet evening on Earth, and what it would and would not mean for us. Begin with the distance, because the distance is everything, as it has been all night. Stephenson 2-18 sits roughly 19,000 light-years away. That is a vast gulf, far across the inner galaxy, and it is the first and most reassuring fact about its eventual death. A supernova is one of the most energetic events in the universe, and if one were to go off truly close to us, within a few dozen light-years, it could genuinely trouble the Earth, stripping at our atmosphere with its radiation. But that danger zone reaches only out to perhaps 100 light-years at the very most. Stephenson 2-18 is 19,000 light-years away, almost 200 times beyond the farthest edge of any concern. When it dies, it cannot touch us. There is nothing in its ending to fear. It is far enough away to be perfectly, completely safe, and close enough still to be magnificent. Because magnificent it would be. A supernova at 19,000 light-years would not be a faint event requiring a telescope to notice. It would be one of the great spectacles a human being can witness. For a few weeks, perhaps longer, a brilliant new point of light would appear in the constellation Scutum, blazing far brighter than any ordinary star, bright enough to be unmistakable, bright enough that it might be visible not only in the dark of night, but in the blue of full daylight, a star you could see with the sun still up. At night it might cast faint shadows. the way the full moon does. People would step outside to look at it. It would be talked about, photographed, remembered, a temporary second beacon hung in the sky for a season before slowly fading back into the dark over the following months. Humanity has seen such things before. Rare supernovae bright enough to startle whole civilizations, recorded by ancient astronomers as guest stars that arrived, burned, and departed. Stephenson 2-18's death, when it comes, would be another of those guest stars, and a spectacular one. But here is the part that asks us to slow down and think a little differently, the strange, gentle truth folded into all this distance. We have been speaking of the star's death as something that lies in the future, and in one sense it does. But remember what a distance of 19,000 light-years actually means. It means the light we receive from Stephenson 2-18 tonight, if we could see it through the dust, left the star 19,000 years ago. We are not seeing the star as it is. We are seeing it as it was, 19,000 years in the past, when the last ice age still gripped much of the northern world, and no city had yet been built anywhere on Earth. Everything we have said about this star tonight, its size, its tenuous fog, its position above the Eddington limit, all of it describes the star as it appeared 19,000 years ago. The light carrying that picture has only just arrived, which leads to a quiet and almost dizzying possibility. The star may already have died. Somewhere out there, 19,000 years ago, is a long time in the late life of a massive star, and we genuinely cannot rule out that Stephenson 2-18 has already reached its ending, already collapsed, already exploded into the supernova we have been imagining. If it has, the light of that death is still on its way to us, still crossing the 19,000 light-years of dusty space between, and will not arrive for many years yet. The star we describe so confidently in the present tense may, in truth, have already moved on, and its final news simply has not reached us. We would have no way of knowing. We are always, with every star, looking at the past, and the more distant the star, the deeper into the past we are looking. There is something worth resting in there, a softness in it, rather than a sadness. The universe does not deliver its events to us all at once. It sends them at the speed of light, which is fast beyond any human measure, and yet, across these distances, achingly slow, so that the sky we see is not a snapshot of now, but a vast layering of different pasts, each star showing us a different age, their light arriving in its own time. The night sky is less a photograph than a long letter, written across thousands of years and still being delivered. And there is one more possibility, gentler still, that keeps even the manner of the ending open. We have spoken as though Stephenson 2-18 will simply die in its current form, a red supergiant collapsing into a supernova. But stars at this stage do not always hold their shape until the end. Some massive stars in their final chapters contract and heat, rather than collapsing outright, shrinking and warming from cool red giants into hotter, more compact stars, sometimes called yellow hypergiants, before they reach their true ending. It is entirely possible that Stephenson 2-18 is not at its largest now, that the vast tenuous fog we have been marveling at all night is a passing phase, and that the star may yet draw itself inward and change its character before the final collapse arrives. The enormous size that gives this star its fame may be a temporary thing, a chapter rather than the whole book, a stage the star is merely passing through on its long way to the end. So we are left holding a star that is uncertain in nearly every direction at once, and there is a kind of peace in that, rather than a frustration. Its size is uncertain, resting on a distance we cannot pin down. Its present state is uncertain, hidden behind 19,000 years of travel time. Even its future shape is uncertain, open to a quiet transformation we cannot yet see. The star we have spent this night describing is, in a real and humbling way, a portrait of something we can only glimpse through veils of dust and time, our best honest reading of a far-off, slowly changing thing whose true present we will never witness, only its long-delayed past. And that, in the end, is not a flaw in the story. It is the story. The not knowing, the veils, the long light still travelling toward us, are the truest part of what this star has to teach, which brings us, as the night begins to settle toward its close, back to the thought that has run quietly beneath everything tonight. Our map of the galaxy is built on gaps, and the largest, strangest things in it are exactly the ones we can see least clearly. That thought, and where it leaves us, is where we go next. Let us step back now, away from this one star, and take in the larger shape of what tonight has really been about. Because for all that Stephenson 2018 is extraordinary, the deepest thing it has to teach us is not about itself. It is about how we come to know anything at all out there in the dark, and about how much of the dark we have not yet managed to read. Think about how we found this star, not through a careful hunt for the largest object in the galaxy, not with a dedicated search sweeping the sky for record holders. We found it almost incidentally. It sat in a catalogue, one numbered entry among many in a cluster catalogued by an astronomer working in the infrared decades ago. It drew attention only because it was too bright to make easy sense, and that very brightness made it suspect, an anomaly flagged and set aside. Its true scale was confirmed not by anyone seeking the biggest star, but by astronomers studying the membership of a cluster, asking the modest question of which stars truly belonged to the family, and which were impostors. The largest star we know of, or very nearly so, arrived in our understanding sideways, as a byproduct of someone carefully checking who was related to whom. And recall how the whole lineage behaved, the long procession of giants we walked through earlier. Betelgeuse, the one we can see clearly, still surprising us with a great dimming nobody had predicted. VY Canis Majoris, its size shrinking not because the star changed, but because we learned to tell it apart from its own shed clouds. UY Scuti, crowned on one distance estimate and then thrown into dispute when a better instrument suggested it was only half as far. Every single correction, in every case, came from a sharper look, rather than from a new object appearing. The stars were always there, exactly as they are. What changed, again and again, was the quality of our seeing. The humbling was never the universe rearranging itself. It was us, slowly, getting better at reading what had been in front of us the whole time. Put those two observations together, and an honest question rises on its own. We have been asking all night how large the largest star is, but perhaps the better question is simpler and wider than that. How many more are out there that we simply have not seen properly yet? The answer, almost certainly, is a great many. We saw why earlier, when we sat with a zone of avoidance, that thick curtain of dust drawn across the crowded inner galaxy, where the most massive stars are most likely to form. The largest, rarest, most extreme stars tend to live in exactly the regions our instruments can see into least well. Our census of the giants is not a complete and confident catalogue. It is a record of the ones that happen to be visible enough, near enough, or anomalous enough to catch our attention through the haze. For every Stephenson 2 to 18, we have managed to measure, There may be others just as large or larger, sitting right now in the dust lanes of Scutum and beyond, already recorded as faint, unremarkable, anomalous entries in some catalogue, flagged perhaps as too bright to make sense, waiting for a sharper instrument or a more patient astronomer to look again and see what they truly are. This is worth saying plainly, because it is not a rhetorical flourish. It is a real gap in the data. Our knowledge of the larger stars is genuinely incomplete, genuinely biased toward the regions we can see, and genuinely likely to keep shifting as new surveys and sharper telescopes push deeper into the obscured parts of the galaxy. The title of largest known star has changed hands several times within living memory, and there is every reason to expect it will change hands again. Even now, the title is not cleanly settled. Some compilations place other red supergiants near the top instead, stars like WOH G64, which sits at perhaps 1,540 solar radii in a neighboring galaxy, depending on which assumptions and which measurements you trust. The honest phrasing is not the largest star, full stop, but one of the largest stars we currently know of, measured as well as we can manage, through all the veils between. And here, before we let the night settle toward its close, it is worth pausing on why any of this matters beyond the simple pleasure of large numbers. Why study these difficult half-seen giants at all? Because they are where much of the universe is made. A star like Stephenson, 2 to 18 in its life, and especially in its death, is one of the great factories of the cosmos. We saw how it climbs the ladder of fusion, building helium and carbon and oxygen, and on toward iron in its layered core. And when it ends in the supernova we imagined, that explosion forges still heavier elements and flings the whole enriched mixture out into the galaxy, seeding the surrounding space with the raw material of everything that comes after. The carbon in a future tree, the oxygen in a future breath, the iron in a future world's core. Much of it is assembled in exactly these massive stars and scattered by exactly these deaths. To understand the larger stars is to understand where the ingredients of planets and life are manufactured. It is not an idle curiosity about record holders. It is, in a real sense, the study of our own origins, traced back to the kind of star that made the stuff we are built from. And to understand them well, we have to reckon honestly with how poorly we still see them. The gaps in our census are not an embarrassment to be hidden. They are a frontier, an open invitation. Every dusty region we cannot yet read clearly is a place where the next surprise is probably waiting. Every anomalous entry flagged and set aside is a question someone may someday answer. The map of the galaxy is unfinished, and that is not a failure. It is the most hopeful thing about it, because it means there is still so much left to find, still so many giants sitting quietly in the haze, already catalogued, already numbered, waiting only for a clearer pair of eyes. So Stephenson, 2 by 18, leaves us not with a settled fact, but with an open door, which is a far truer gift. It is a reminder that our knowledge of even the most enormous things is provisional, that the universe is larger and stranger and less fully mapped than our tidy catalogues suggest, and that the limits we draw with such confidence are nearly always, in time, gently exceeded. We thought stars topped out near 1,500 solar radii, and one turned up well past it. We thought we knew the largest, and the title kept slipping. We will think we know again, and the universe, patient and vast and only half revealed, will almost certainly have something waiting on the far side of whatever line we draw next. There is nothing unsettling in that. There is, if you let there be, something deeply restful in it, a sense of a cosmos roomy enough to keep surprising us for as long as we care to look. And that gentle thought, that the edge of what we know is soft and always receding, is the right place to begin coming home, back from the dusty reaches of Scutum, back across the long light years, back to the quiet room where you are resting now. That return, the soft landing, is where we go for the last of it. So here we are back home. We have travelled a long way tonight, out past the planets, across 19,000 light years of dust, to a star that reaches towards Saturn and holds 10 billion suns of empty room. And now, gently, we come back across all that distance, back through the haze of Scutum, back to the small, steady ground beneath you, the weight of your own body resting where it rests, the slow and easy rhythm of your own breathing in a quiet room. And it is worth saying, as plainly and as softly as anything tonight, that none of what we have explored changes a single thing about this moment. Stephenson 2-18, whatever its true size, however far past the old limits it sits, does not alter the steady turning of the earth beneath you. It does not change the warmth of where you are lying, or the air moving in and out of you, or the fact that tomorrow the sun will rise over your particular patch of the world exactly as it always has. The vastness of that distant star and the smallness of this present moment are not in conflict. They simply belong to different scales, and both are true at once, and there is room in the universe and room in a single quiet evening for both. If anything, the journey changes only one thing, and it is a small and gentle thing. It softens the edges of our map. We began the night with a crisp-sounding question. How big is the biggest star? The kind of question that expects a hard number for an answer. And the further in we went, the softer that question became in our hands. We found that the star's size rests on a distance we cannot pin down. We found that its very surface is not a surface at all, but a slow fading of glowing fog into the dark, with no real line to measure. We found that it sits past a limit our simplest equations drew, not because the equations are broken, but because they were written for tidier stars than this. And we found that the title of largest itself keeps slipping, past and revised and disputed, never quite settling, because the galaxy is so much larger and dustier and less fully seen than our catalogues pretend. Every firm edge we reached for all night long turned soft when we touched it, and that, it turns out, is not a disappointment. It is the truest and most beautiful thing the star had to give us. Because every limit we have ever drawn with confidence, the universe has eventually answered with something quietly waiting on the far side of it. Not with a thunderclap, not with a rebuke, but gently, in the data, in a number revised, in an anomaly that turned out to be real, in a star that sat calmly above a ceiling it was not supposed to be able to cross. The cosmos has never seemed to feel bound by the lines we sketch across it. It simply keeps being larger and stranger and more open than we expected, and it reveals that not all at once but slowly, patiently, one careful measurement at a time, the way the truest things tend to arrive. There is one last softness worth resting in before we let the night go, and it reaches all the way from that distant star to you. We spoke of how a star like Stephenson 2-18 builds heavier elements in its layered heart, and how its eventual death scatters them out into the galaxy. Carbon, oxygen, the very atoms that go on to make planets and oceans and living things. Those elements did not come from nowhere. The carbon in your body, the oxygen you are breathing right now, the iron carried in your blood, were forged long ago in the hearts of massive stars not so unlike the one we have followed tonight, and flung out into space by their deaths, and gathered up eventually into the world that made you. You are, quite literally, assembled from the ash of ancient giants. The same kind of star we have been gazing at across all that distance is the kind of star that, generations ago, made the stuff of you. So the great soft star in the dust of Scutum is not really so far away after all. Its kind is in your hands, in your breath, in the slow beat of your heart in the quiet. The distance between you and the giants is real, 19,000 light years of it, and yet the substance is shared. You are listening to the story of your own distant origins, told slowly in the dark as you drift towards sleep. And that is a fitting place to let everything settle. A star whose own edge is a gentle gradient, fading softly into the dark with no clear line to mark its ending, is exactly the right thing to end a night on. There is no hard boundary out there to mark where the star stops. And there is no hard boundary here either, between waking and sleeping, only a soft fading of one into the other, a slow drifting from the lit world into the dark, as gentle and as edgeless as the outer fog of a supergiant trailing off into space. So let the numbers go now. You do not need to carry any of them with you. Let the 2,000 solar radii, the 10 billion suns, the 19,000 light years, all of it loosen and drift away like the star's own outflowing wind. Let your shoulders rest a little heavier. Let your breath slow to wherever it wants to go on its own. Somewhere far out in the dusty inner galaxy, a vast and gentle star is glowing softly in the dark, holding its loose shape, shedding its quiet light, reaching towards Saturn and trailing off into the cold, with no edge anywhere. It asks nothing of you. It has been there, in some form, far longer than we have, and it will go on long after this night is over. And you can simply rest beneath it now. The universe is wide, and its boundaries are soft, and there is nothing out there in all that vastness that you need to hold on to tonight. Let it all become a faint, warm haze at the edge of sleep. Let the great star dissolve gently into the dark, and let yourself drift softly all the way down.